that also already in the presentations I made. This is normally just how it looks like. You start at around 20 degrees, then go to 40, 60, 80, whatever, and then yeah. So what we see here is somehow after 150 minutes, this is the time where the liquid, where the collector broke, or so then we got almost no flow anymore. Yeah, which is not so good for the components. We should try to avoid these things.
So it didn't even reach 100 degrees?
No, it was, I think, at 90. So 90 was too much for it. But actually the day before I was at 100 was the collector. So I think 2 days in a row going to 100 degrees C killed the materials.
But only it was the collector or the.
It was
it
was a fitting. Yeah. So what I did then is also to take away all the data we can't use. Normally, even these data would not be usable. Is what I said. This is always in the 15-minute range where it gets stable. Normally, you would also throw all these data away, but we have not enough time, so I took some of the data still, which is available, because we have not shifted, we have not reduced the distance in the beginning, so I couldn't also not consider the 20-degree measurement values, so I just considered the 40, 60 and 80. So that's just 40, 60, 80. You see the mass flow is stable on the entire time. This looks close to that what I showed you in the presentations.
Yeah.
Maybe we have a short look. What I did is this is what I said already is a measured irradiation. That was the collector size. I don't know if that's true, but I just put something in here. What I like to do is, as I said already, to calculate the time which was passed during the test. So yellow is all which is calculated. Then I calculated the delta T over the collector. So T out minus T in. That's pretty short, pretty easy.
This computer.
But it should be the same if I try to reach this one or that one. Right. I was okay. Too many computers. So then I already also calculated the mean temperature, which is the middle temperature of the collector. I know I'm not 100% sure, but if you have closed loop air collector test, they calculate the mean temperature in a different way, I think. They say, when I'm right, I'm not 100% sure about that, they say the collector is not, if you have a water collector here, they say just, if here is inlet, and here's outlet.
Exponential curve.
Yeah, for water collectors, they say I think it's like this. The temperature decrease is like this.
Linear, yeah.
Linear, and I think they say for water air collectors, it is more like that.
So it's a different average. There's an average for that.
Yeah, that's
a long-based average. I forget what it's called.
Yeah, and they considered that also for the efficiency curve determination, because you have to calculate this T mean value.
Yeah.
And so this is why they do that for air collectors in a different way than for water collectors. I've not done that yet, but there will be a hint in the ISO 9806 how to calculate the temperature, the T mean value for the air collectors. What's in the wrong? Stupid. I calculated the power in watt again. Here is only kilowatts. That's by CV mass flow and the delta T. Then by taking
Very good.
by taking the power output and by considering the measured irradiation and the collector size, I can calculate the efficiency at that moment. It's only the efficiency at this moment. And then for making the efficiency curve, you have to calculate the reduced, they call it the reduced temperature, the reduced temperature, I don't know what they call it, TM star, the reduced temperature, whatever. It's actually the mean temperature minus the ambient temperature, the reduced temperature difference related to the irradiation.
Oh.
I can.
Hmm.
That's
Temperature over radiation. Watts. Temperature over watts. Per meter squared.
so see, that's exactly that. T mean minus TA divided by the irradiation. So that's the reduced temperature. And by putting that according to the efficiency, which we calculated at that time, you see the efficiency related on the TM star. This is
You
that
get a
X and Y. That
nice
gives you
linear relationship. Is this efficiency, the vertical axis?
This is sorry, that's efficiency.
Yeah.
That's actually what I did here as well. I just
Okay.
made the dots over here. And just in order to show that there is a difference, one is made on ambient, based on the ambient temperature, and the other one is made on the ventilation temperature. So just in order to, this first thing is based on the ambient temperature, and the second one, and the second one is based on the mean temperature of the ventilation units.
What's the difference within the two ventilation units? Temperature difference?
1 degree, 1.5.
Oh, could that high? Okay, because of the ventilation.
Yeah,
cold
because
air is from one side.
Yes, this is why the one is colder than the other one.
We might have to install our own RTDs to replace that. Because the two sensors are not exactly the same location as the air blowing over the specimen.
Why? They're installed directly in the air.
But it's not.
Yeah.
just,
Okay.
Yeah, you know what I mean?
You know, I know
Yeah.
what you mean. But
Yeah.
I know what you
But it's better than nothing right now.
mean.
Yeah.
Yeah. Okay, and then in the end, you would get out these points, and by fitting these curves, then you can get your efficiency factor. I did not do that because it makes no sense, because the curve will not be like this. It will more in this points. It's normally flatter. So
How do you get a 0 point?
huh?
How do we get a 0 point?
Zero?
Yeah.
This one?
Yeah.
If you measure, if your if TM star is
The same
if
as,
you show if you T mean by T ambient, So you will never go exactly to that, but if
But
you
as
set a
close as
temperature,
possible.
like inlet temperature of 20 degrees or 19 or 18 degrees, something like that, you will go close to the 0 point
Okay.
in order to calculate your efficiency factor. Maybe
Okay.
15 degrees also would also be possible.
Mm-hmm. All right.
Okay? Got that?
Yeah.
So I would say we disassemble the collector and
Yep.
the air collector, and then we can also already do some preparations for the afternoon training. When is lunchtime?
12.
12.
We still have 14 minutes.
Yeah, so we
Yeah,
can
that's
prepare these things for
Just press
for
there.